So worksheet number 4 is velocity versus time graphs and displacement. And so for this one, we're going to focus not on speed, but on velocity, where we're worried about the magnitude and the direction. So remember, let's see, I'm going to write magnitude plus direction. Remember that we're looking at two different types of things when we're looking at speed or velocity. One is called a scalar, and one's called a vector. We're going to work with a lot of things that are vectors in physics class. Things that are scalars so far include distance and speed. Things that are involved in the magnitude of something, but not necessarily the direction. Vectors include the direction and the magnitude. These are things that include so far displacement and velocity. So they're related, but they're not exactly the same. All right, so we're going to look at a couple different representations of motion here. We have a motion map. There's a place here for position versus time graph. There's a place for a velocity versus time graph, and then a place where we can describe what the motion of the object is like. So we start with our motion map, and we see that we've got arrows, and all the arrows are the same length, which is what we expect, because remember the theme for our unit is constant velocity. So we expect them all to be the same. So here it says describe the motion of our object. So remember, for descriptions, the first thing we want to say is where our object starts. So I'm going to say object starts at 0 meters. And then our object is moving with a constant velocity. And we can look at this and figure out what that velocity is. I'm going to go ahead and label these with times. This first one is time equals 0 seconds. Remember, don't label that 1 second, label it 0. Second one is t equals 1 second, then t equals 2 seconds, t equals 3 seconds, 4 seconds, t equals 5 seconds. Okay. So now our object is moving at a constant velocity. And what is our constant velocity? Can we say what it is? How many meters per second are we traveling? Yeah. 2 meters per second. So every second, our object advances 2 meters forward. So we say moves 2 meters per second. In what direction? That's tricky, right? So for number lines, we're going to go either in the positive direction or the negative direction. So here our object is moving 2 meters per second in the positive direction. And then we're going to say where it stops or how far it goes. So our object stops at 10 meters after 5 seconds. Could you draw a motion map if this is what the information you had was? I think so. All right, so next we're going to represent that motion with a position versus time graph. Remember, when you see this X, that means position. That's why it's over here, position. So first thing we need to do is decide how we're going to spread out our axes. I think with only 5 seconds of time, we can just go across here one for one. 1, 2, 3, 4, 5. Yep. 1, 2, 3, 4, 5. I like to go ahead and do my set up the next one too, if I can. So here I'm going to mark these 0, 1, 2, 3, 4, 5. So there's my time. For position, my change of position is going to be from 0 meters up to 10 meters. I'm pretty sure I don't have 10 lines here. So I'm going to stick with 2. So the first one will be at 0. I know that. And then 2, 4, 6, 8, 10. Yeah, that'll work nicely. 2, 4, 6, 8, 10. Now my dots. When time is 0, I'm at 0 meters. So there we go. At 1 second, I'm at 2 meters. At 2 seconds, I'm at 4 meters. At 3 seconds, 6 meters. 4 seconds. You guys ever notice when you're doing these in this unit, you get to the point where you can predict where the next one should go? Isn't that cool? There we go. This looks like a straight line. And remember, the slope of this line is the velocity of the object. So to figure out our velocity, we need to look at our slope. If we put our slope-o-meter on this, is this positive, negative, or zero? Positive. It's positive. So we know that it's going to be in the top part of our velocity versus time graph. And then we can figure out a value for this. If I just look at my first and last data, I'm going to say my change in position divided by my change in time is going to be equal to 10 meters minus 0 meters divided by 5 seconds minus 0 seconds. And I've just taken these two data points here. That's telling me that my velocity is 2 meters per second, which matches what we said up here, 2 meters per second. So when we go over to our velocity versus time graph, we just have to label one of these as plus 2 meters per second. Right? So if I label that 2, it's 2 meters per second. And then I can just draw a line all the way across here because in looking at this, I know that it's constant. The slope down here is the same as the slope up here. Slope doesn't change. If I look at my motion map, I can see that I've traveled 2 meters in this second, 2 meters in the next second, 2 meters in the next second. So my velocity is the same all the way across my motion map. So I'm confident when I draw my line here that this should be a straight line at 2 meters per second. Do you guys have any questions about those so far? No? Okay. So then it says write a mathematical expression that represents the relationship between position and time. So not this one, this one. And we know that that's a line, right? Y equals mx plus b. But we need to replace some of these things. So y is going to be our position. Our units for the position are meters, equals the slope of our line, which was 2 meters per second, times our x variable down here on our x-axis. So it's going to be times time, measured in seconds, plus our intercept, which here is 0. Another way to think about this is that we've got our position in meters equal to, and we've said this before, this number right here is our velocity. So our position equals our velocity, meters per second, times time in seconds, plus another way to write where your y-intercept is, or your initial position, right? Because this is, our intercept here is going to be our starting point. So since it's a position, we're going to use x because that's the symbol for position. And then a subscript 0, which means it's the position when you start. It's your position when time is equal to 0. So this is a more general form of that. The way the question is written, it's asking for this one on the left. But this is a more general form that may help you solve problems. It says from the position versus time graph, find the displacement from time equals 1 to time equals 3. So if we're going to just look at a specific interval, we want to know what's happening between those 2 points. Trying to grab a highlighter. Okay, so between 1 second and 3 seconds, we're looking at the interval between those 2 points. So the displacement between those two is whatever the change in position is. So we're going to look at the position at 3 seconds minus the position at 1 second. So 3 seconds, our position is 6 meters. At 1 second, our position is 2 meters. And so the displacement then is going to be 4 meters. Lastly, it says, find the area under the velocity versus time graph from 1 second to 3 seconds. So to find the area, we're going to be looking at this space under here. think you guys can see that on the screen there. So if we try to figure out that area, we know that each of these boxes is 1 second long and 1 meter per second high. So if we've got 1 meter per second times 1 second, that means that the area of each box is 1 meter. So this represents 1 meter, this one represents 1 meter, this one is 1 meter, this one is 1 meter. So those boxes represent 4 meters. That area under that box or under that curve represents the displacement of the object in that range of time. Right, this area represents displacement. So we could go from velocity versus time, the velocity versus time graph, to the position versus time graph if we needed to. All right, what questions do you guys have about problem number 1? Any questions?